Assalamu alaikum.
Walaikum salam.
Okay, so welcome to the class of microwave engineering. Okay, so we have only two students who have joined this class. So not many students are interested in taking classes. Anyway, let me continue with today's lecture. Okay, so one of the important issue in microwave engineering is impedance mismatching. So as a microwave engineer, you will encounter this problem that your circuit is not efficient in terms of power, because not all power of microwave source is delivered to the load. So as a microwave engineer, you know that this problem can be solved with the help of circuit that is known as impedance matching circuit. Okay? So this is the problem, and solution is or they are also known by the name of impedance tuning circuits. So this is the solution. Now, one of the impedance matching circuit we have already discussed in our last class, and that was quarter wave transformer. But there are also some other impedance matching circuits that we will talk about today. So types. So one of the type, as we have already discussed, is quarter wave transformer. Then the other circuit that we will talk about today is stub. And third one is L network. So these are commonly used types of impedance matching circuits. Now, these circuits can be further uh, categorized into their sub-circuits. So quarter wave transformer, it has actually two variants. One of them we have already discussed, but that particular circuit is known as single section quarter wave transformer. Single section quarter wave transformer. But there is another type of quarter wave transformer that is used because of some reason that we will discuss, and that circuit is known as multi section quarter wave transformer. Similarly, this stub, it can also be divided into two types. One is known as single stub, and the other one is known as double stub matching circuit. L network, it also has two types. There are no specific names, but we can call them, we can just give them notation that there is L network number one and there is another network that is L network number two. So we will discuss what is the difference between these two. Okay. So let's discuss as well as design these types, these impedance matching circuits one by one. So let me start with the L network. Okay, L network. So what is basically L network? Okay, this L is an abbreviation for lumped. Okay. And the reason why it's called lumped network because it involves use of lumped elements. And what are the lumped elements? That is capacitor and inductor. So it uses lumped elements, that is capacitors and inductors in a specific configuration. So the idea behind this circuit is that with the help of capacitor and with the help of inductor, you can match your circuit. Okay. So let's talk about the two configurations. I am talking about specific configuration. It means you have to connect capacitors and inductor in a particular configuration, as well as it's also important to find out what will be the value of the capacitor and inductor. You cannot just use a 1 microfarad capacitor or 1 nano Henry inductor and your circuit will be matched. No, it's not like that. You have to find the specific value of capacitor and inductor. So we are going to talk about the design procedure, step-by-step design procedure that you can use to match any circuit with the help of capacitors and inductor. So what are the two possible configurations? So let me draw them and then we will find which of the configuration will be used in a particular case. So let's assume that this is our main transmission line with a characteristic impedance Z0, and we want to connect this transmission line to a load, but that load is not matched. So let me represent the load by its impedance. This is our load. So the problem is this ZL is not equal to Z0. So I don't want to connect this load to this transmission line directly. So I don't want to connect this load to this. I want to use some kind of a circuit in between load and this transmission line so that my circuit appears to be matched. So this is how you will connect. One of the possible way is, or I will represent this with a general notation. So there will be one lumped element, let's say represented by its reactance X, and another lumped element will be connected in parallel and it will be represented by its susceptance, which symbol is B. And this is the circuit that we will connect in between load and transmission line. So the circuit that you can see over here, this one, this is your L network. So By specific configuration means that you will connect one component in series and other component in parallel. Okay, so this is let's say you can call it L network number one. If you go back, I mentioned that there are two possibilities, L network number one and two. So let me call this one as one and the other one. What is the other possibility? So it is also possible that you may start with this, that there is a transmission line Z naught, and I want to connect this with a load, but because load is different than Z naught, so I don't want to connect it directly. So the other possibility is I can use a circuit such that the first element is now in parallel configuration. So this B is the susceptance of maybe it may be inductor, it may be capacitor. So we will talk about whether this B is a capacitor or inductor. This is what you will find as a design parameter. And the other element will be connected in series. So for series we use inductance, sorry, reactance. So now this is other possible configuration. So this dotted line is another network, L network, and we will call it L. So now, coming to the design process, as a microwave engineer, how you will decide whether L network one will solve the problem or L network number two will solve the problem. And once you make this decision, then the next task will be to find out what is X and what is B. What is B and what is X over here? In case you selected L network number one, then you need to find out what is this X and what is this. We know that this X and B, it may be capacitor, it may be inductor, but we don't know whether this is capacitor or this is capacitor, whether this is inductor or this is inductor. So what are the possibilities? Possibilities are this, let me, so this can be capacitor, this can also be capacitor. So both of these can be capacitor. There is a possibility that this is inductor, this is also inductor. So second possibility. This is capacitor, this is inductor. This is third possibility. What is fourth possibility? This is inductor and this is capacitor. So when you start designing this L network, there are four possibilities. Okay, capacitor, capacitor, inductor, inductor, capacitor, inductor, inductor, and capacitor. Similarly, if you select L network number two, so again there are four possibilities for B and X. So let's find out how you will find out the specific uh, type, whether this is capacitor or this is inductor, because only one possibility, there will be only one solution. That is what I'm talking about. So, so now we are going to talk about the design process. So for L network, there are two tasks. The first one is selection of suitable L network, which means L network number one or L network number two. And once you made this decision, the second step will be what are values of X and B. So there are two options. We can solve this design problem either using equations, which is known as the analytical method, and a second option is you can perform these two tasks using Smith chart. And this is what we are going to discuss, because our focus is that students should be comfortable solving such type of problems with the help of Smith chart. Okay. So let's answer the first question: how you will decide what whether L network number one will solve the problem or L network number two will solve the problem. The answer to this question will be based on the location of the impedance. So of course, whether L network number one or L network number two will be used, that is very much dependent on your load. So once load is given to us, then we will be in a position to answer this question. So the question is, how given load value will help me to decide whether this load will be matched by L network number one or L network number two. Okay. So as we are using Smith chart, so I'm only talking about the Smith chart solution method. So how you will answer this question with the help of Smith chart. Now, whenever you use Smith chart, so we only talk in terms of normalized values. Okay, we only talk about normalized values. So the first thing you will do is to normalize your load. Okay, so what you will do, you will normalize the load. So what is the meaning of this statement? You will take the value of load impedance, whatever value is given to you, and you will divide it by Z naught. So this will give you a normalized value, which means there will be some real part. So let me represent that by RL, and there will be some imaginary part, that is XL. Then what you will do? You will locate this normalized load on Smith chart. So we will, once I mention all of the steps, then we will solve one problem, and then you will see the application of all of these steps. Okay. So once you have the normalized load, you will find the location of this load on Smith chart, and this is something which we have already covered before midterm. You know how to find the location of any impedance. That is, you need to find out the resistive circle for this value and the reactive circle for this value, and the point at which these two circles will be intersecting, that will be the location of the impedance. So this is a straightforward procedure. Now, once you locate this normalized load on the Smith chart, then what you need to observe is whether this normalized load is inside 1 plus jx circle or outside 1 plus jx circle. So what you are going to do is find out position of normalized load with respect to 1 plus jx circle. So there are two possibilities. If it is inside 1 plus gx circle, then which of the L network you will use. And if it is outside 1 plus gx circle, then which of the network you will use. Okay. So this is the question that we need to answer. So if it is inside, then select L network number 1. And if it is outside 1 plus gx circle, then select L network number 2. So I'm talking about this network. If this load is inside 1 plus jx circle, then you are going to match your circuit with the help of this configuration. And if this load is outside of 1 plus jx circle, then you need to use L network number 2, which consists of this type of configuration. So this is how you will be able to decide about the selection of suitable L network. Once you do this, then the next task will be to find out. Let's assume that you have a situation where the load is inside 1 plus jx circle. So you will draw this circuit to, to give this information that this is the network which you will use as a microwave engineer. Now you are going to find out what is X and what is B. So as I mentioned in my previous discussion, that this X and B, there are 4 possibilities. So we need to find out which is the, out of those 4 possibilities, which is the exact single possibility. Okay. So let's find out how you are going to find this value. So we will use Smith chart. So how you are going to find B and X? So again, there are 2 methods, either analytical method. So there are some equations which are given in the book. So with the help of those equations, you can directly find the value of X and B. But what we are going to do is, without using any equation, but using Smith chart, you will be able to find X and B. So what you will do, you will use graphical method to find X and B. And you can see why I am representing this by small x and small b, because of the reason whenever you use Smith chart, all quantities are normalized. Okay. So in circuit, you have capital X. But when you use Smith chart, first of all, you will find out small x, which is the normalized value of this reactance. Similarly, in circuit, I am representing susceptance by capital B. But first of all, we will find out B, that is normalized. Once you know normalized quantities, then it is very easy to find out the actual quantity, because you know that which quantity we are using for normalization, Z naught. So how to unnormalize it? Of course, we will use Z naught for unnormalization. Okay, so normalized quantities. So this is the whole procedure that I have explained from conceptual point of view, that how to use L network for matching. Okay, so now let's do one example so that you can understand all of these steps. Okay, so now we are going to one example. So let's assume that there is load ZL and it is equal to 200 minus J 100 ohm. It is connected with the main transmission line with the characteristic impedance Z0, and Z0 is 100 ohm. So what, as you can clearly see that ZL is not equal to Z0. So there is impedance mismatching. So what we are going to do is design an L network. Design an L network to match the load at, so which frequency we are using in our circuit. So at a frequency of 500 megahertz. So now this is the problem, or this is the type of problem that you will find uh, from L network point of view. So as we are using Smith chart, so how you will proceed? The first thing is you will normalize your load. So let's represent the normalized load by small zl. So zl divided by z naught. That will give you 2 minus j. So this is our normalized load. And if you go back, this is what I asked you. What is the first thing? Normalize the load impedance. That is this. So this you can see RL is 2 and XL is minus 1. Okay. RL is 2, XL is. So what you need to do is find the location of this. So locate it on Smith chart. So let me share the Smith chart with you. Okay, so the load is, what is the value of normalized load? ZL was equal to 2 minus J. Okay, we need to find out a resistive circle for 2 and a reactive circle for minus 1. Okay, so uh, now you people must be comfortable with finding the location. But let me, okay. So where is the resistive circle for a value of 2? So you can clearly see this is the circle for 2, this one. You can see I can mark it. This is the resistive circle for 2. Okay. And where is the minus 1 circle? So you all know that we need to look at the bottom because this is a positive region, this is the negative region. So we need to find out where is this. So this is the circle for what? This one. So you can see this is 1 written, and this means that this is the point. So where these two circles are intersecting, so if someone is still confused, let me draw it. So what you will do, you will find out. Okay, so this is the resistive circle. Again, you don't need to mark it on your Smith chart. I'm just drawing it for your understanding. Okay, and then you are going to find out the resistive reactive circle, which is this one. So where they are intersecting, they are intersecting at this. So it means this is the location of your ZL. Now, what was the second task that we need to do once you locate ZL? So now we have done our first part. Okay, we have located. So now we need to find out what is the location with respect to 1 plus jx circle. Now, where is the 1 plus jx circle now? Whenever I use this terminology, 1 plus jx circle, it means I'm talking about that particular circle for which the resistance value is 1, but reactance value is changing. 1 plus jx means that resistive circle is constant. It is 1, but reactive circle is x, so it means it can change. So where is the resistive circle for a value of 1? So it's obvious this is the circle. They can write 1 is written. So I am actually talking about this circle. You can see resistive value is 1, but as I am moving, so x is changing. So this whole circle, which you can easily identify on your Smith chart. So actually, I'm talking about this 1 plus jx circle. Whenever I use this terminology 1 plus jx circle, it means I'm talking about the circle. So the question was how you are going to decide which L network you are going to use. You need to find out whether the normalized load is inside 1 plus jx circle or outside. In this particular example, it's obvious that ZL is over here. So it means it is inside. So when L network, sorry, when impedance, normalized impedance is inside 1 plus jx circle, then what we are going to decide? We are going to decide that L network 1 is going to be used. So what is our selection? Our selection is L network number 1. And how that network look like? So if this is main transmission line, so L network means we have X, we have B, and then it is connected with our load. So it means now this is the circuit that you will solve. Okay, so we have completed step number 1. Okay, let me. Okay, so let me go back. Yes. So what we have done, we have normalized the load impedance. We have located this normalized load on Smith chart, and then we find out its position. And what we observed, we found that it is inside. So if it is inside, then select L network number 1. So where is L network number 1? This is our L network. Again, just to make thing that you understand this whole process, if you are given an example such that after locating normalized load, you find that it is outside of 1 plus jx circle. This is another possibility. So in that case, your choice will be L network number 2, which means now you will solve this circuit. So make sure that you select the proper L network number 2, because when impedance is inside 1 plus jx circle, then only this circuit will match your load. If normalized load is outside of 1 plus gx circle, then you have to use this one. What I'm saying is, in case ZL is inside 1 plus gx circle, and rather than using this circuit, you selected this one, it means you are not going to solve the problem, or your problem will never be solved. For other words, from examination point of view, you will get 0 marks. Okay. So now let's move on to the next part. That is, once you selected the proper L network, how to find out the values of X and B. Okay. So how to find out the values of X B using Smith chart. Okay. So we will be using Smith chart. So let me again share the Smith chart. So this is the chart that you will be using to further find the values of X and B. So as I mentioned before, you need to find out the normal, you need to first find out the normalized values. Okay. So small b and small x. So small b means that this is normalized susceptance, and small x will mean that this is normalized reactance. Now, before I move to the next session, because we just have 2.5 minutes remaining in this slot, you should, again, this is something which is basic stuff which you might have learned in your basic electrical engineering, that uh, if B or X is given to you, then how you will find whether it is a capacitor or inductor. So we know from our basic electrical engineering that for inductor, reactance is positive. Okay, so if the value of X is positive, it means this is inductor. And if the value of X is negative, then we know it is a capacitor. What about B? For B, if the value of B is positive, then it means this is capacitor. And if the value of B comes out to be negative, then it means this is inductor. So if you remember when I was talking about that L network, which consists of X and B, so whether this X is capacitor or inductor, so of course, how you will find out it is capacitor or inductor, the value, where the sign of the value, the sign of this number will tell you it is capacitor or inductor. So in case if this X comes out to be +2, then it means we have to use inductor over here. So this will be some kind of inductor over here. And in case X is some kind of a negative number, so if X is equal to, let's say, -3 something, so it means at this position you will use capacitor. Similarly, if the value of B is positive, then it means you will use capacitor over here. And if the value of B is, let's say, negative, -2, then you will use inductor over here. So this is something that you should be familiar with. And we will continue with this example, the example that we are solving. We will talk about this, we will further solve this example in the next session. So let me move to the next session.